So the plan today is just to briefly recap what we saw up to now. And then I just want to mention briefly an important sort of generally applicable limit from unitarity. And then we'll move on to the main topic of this lecture, which is generating the asymmetry. Yeah? So recap. So we saw in the symmetric case with distinguishable particles that the yield from freeze out is approximately equal to this. Okay, and this should match observations. And because we have x not equal to x bar, the observed density over the entropy density today, and this factor is 0.43 electron volts. Okay? And this factor lambda has the Planck mass in there, the dark matter mass, sigma n, our approximate cross-section, thermally average cross-section with the temperature dependence factored out, and this factor G star effective. Okay? Good. Now, you can see that when we set this equal to the observed abundance, the M dark matter cancels out. So then the question is, does this hold to arbitrarily high masses? Okay? And the answer is no. Okay? Given the assumptions we make, in this dark matter scenario, we can't go to arbitrarily high mass. And the reason is follows. There's a limit from unitarity of the S matrix, which tells you that the inelastic, okay, you expand the cross-section in terms of partial waves, where J labels the momentum of the total angular momentum, okay? And in the scattering, this is going to be preserved, yeah? The total angular momentum is a good quantum number. And there's a limit which one can derive with a bit of effort, that this cross-section here, the partial wave, the cross-section of the partial wave is limited to this value here, where J is 0 angular momentum and so on. J equals 0 is 0 angular momentum and so on. Yeah? So, and that J equals 0 is like S wave, J equals 1 P wave, J equals 2 D wave, so on. Yeah? Now, apply this to our dark matter scenario where each of our dark matter particles in the non-relativistic limit has momentum M dark matter V rel on 2. Yeah? You can go in the center of mass frame, then each has half the relative velocity. Yeah? Okay? So then substitute this in, and then you just find that for our non-relativistic freeze-out, we'll have a limit that each partial wave is limited to be smaller than 4 pi to J plus 1 on M dark matter squared V rel, okay? Now, an intuitive way of understanding this is that, of course, okay, we start off with a theory where the probabilities are conserved and the S matrix is unitary. Now, if you want to go to an arbitrarily high cross section, okay, then we do some perturbation theory usually, yeah, and calculate a cross section, yeah. Now let's say you want to go to arbitrarily high cross section, then typically you're going to have to take the couplings very large, yeah. So then your perturbation theory is going to break down, yeah. And so if you just naively take the cross section, you take the coupling very large, then you'll get your perturbation theory breaks down, and you can also get naively a violation of this unitarity condition, yeah? But then a limit comes about, okay? If you take the thermal average of this, okay, you're going to get you can rewrite this in terms of our variable x. Okay. Now, just you can substitute this into this lambda symmetric, yeah, and find then what your maximum possible dark matter mass can be, yeah, because we learned from here that the cross section here is to a good approximation constant, yeah, the required cross section. So of course, if you go to very high dark matter masses, you want to have an approximately constant cross section, but here this m dark matter squared is always getting larger, yeah. So eventually you hit the unitarity limit, okay. So one can do this exercise. So just substitute this into our expression here, set it to the observed abundance, and you'll find that okay, that can be a small exercise, yeah? If you want to check through it. On root 45, xf to the 1/2, okay? Now, you do the exercise, and say you take, assume your dominant cross, contribution to the cross section comes from the j equals 0 partial wave. Yeah. Then you'll find that x freeze out is approximately 28.5 or so, and that your dark matter is limited to be below about 140 TeV, yeah? So this is sort of a very generic argument for why if the dark matters come into thermal equilibrium, and then given the assumptions we've made of no additional entropy production and so on, you can't get this thermal relic abundance much higher than 100 TeV or so, yeah? Now you might ask, okay, but this is just the one partial wave, yeah? So in principle, multiple partial waves can sometimes contribute, yeah? So then we can write that M uni, the symmetric one, is the j equals 0, 1, which we just derived, this 140 TeV, times root 2j plus 1. So if we had solely one partial wave contributing, and if we had multiple ones, if we have, okay, we have this sort of limit. Okay. And I should point out that this sort of velocity scaling doesn't, if you write down a model, it doesn't necessarily apply to each model, yeah? It's sort of a maximum, yeah? So this sort of velocity scaling is typical in models where you have a light mediator, creating a Sommerfeld enhancement for the annihilation, yeah? So for example, if you go to a dark QED-like model where your dark matter is annihilating to some dark photons, then this is a non-relativistic, in the non-relativistic limit, say you send off, imagine you have some dark matter particle and some anti-dark matter particle, and now they're charged under this dark U1, yeah? And they're traveling, the wave packets are sort of approaching each other from infinity, but they're non-relativistic, yeah? So then this guy sort of sees this guy coming, sees the potential, right? So you end up getting the possibility of exchanging dark photons. And this leads, when you resum these sort of diagrams, you get this Sommerfeld enhancement with this 1 on VREL scaling, okay? Yes?
It looks like so suppressed. You have all coupling 1, 2, 3, 6, 7, 8 in the order of 8.
Yeah. You have to imagine this. These diagrams. It's a ladder diagram, so they all contribute, and it's in this limit where the dark fine structure constant is larger than when this is larger than 1, you get an enhancement. Yeah. So you can think of lots of virtual photons being exchanged, yeah, as these approach each other.
But I will do a more simple question.
Yeah.
Why do you want to work with so problematic theory?
It's not problematic. It's just electrodynamics. Yeah. If I replace this with E minus and E plus, and replace this with a photon, when you send the particles to each other, there'll be an enhancement at low relative velocities.
No, I'm thinking about a so huge coupling.
It's just, okay. The question we're interested in is, if you want to go to large dark matter masses, then you want to keep the cross-section roughly constant, yeah? The cross-section scales as, without the Sommerfeld enhancement, the cross-section goes as alpha dark squared on m dark matter squared, yeah? And so when you go to large masses, you want to keep this constant, you'll reach a point where alpha dark is large, and then this will become important. Yeah? And then if you do things carefully, also bound state formation and other effects also become important, and also contribute to this would be j equals 0, and then it also contributes to the j equals 1 partial wave. Okay. You get additional contributions, okay. But this doesn't happen in each model. But if you want to approach sort of this unitarity limit, you tend to get such Sommerfeld enhancement effects, which you can just see that you have to recover this scaling as well, right? Velocity. Okay.
Just to clarify,
Yeah.
just a question. Is it important because I'm a bit confused. You say the x not equal x bar, is it relevant or? Well, I thought this is.
Yeah. So what happens is if you have a Majorana particle or something like this, then you don't have this factor of 1/2, and then you just get a different, instead of getting 140 here, you get something like square root 2 times that.
Okay. So basically, just a
Yeah.
factor.
Okay. Okay. Now, in the case of asymmetric dark matter, we saw yesterday that we need a large annihilation cross-section, which implies that the unitarity constraint also becomes stronger, okay? So then we had this rewriting what we had yesterday in terms of the WIMP cross-section. Remember, we had this formula for R infinity, where R infinity depended exponentially on this ratio, yeah? Okay. So if you just rewrite that formula to like this. Okay. Now, we'll need a larger cross-section. So depending on R infinity, we'll hit the unitarity limit at a lower mass, okay? And it's just a simple exercise, but I'll just give you the result in the interest of time. So then M asymmetric dark matter uni is equal to the symmetric case times a factor that goes as 1 minus R infinity on 1 plus R infinity log 1 on root R infinity. Okay, the steps are given in the notes if you want to follow through the calculation. So to sketch this, and this constraint will apply to very many asymmetric dark matter models. Okay, so this is why it's something sort of generic and therefore good to be aware of. Yeah. So if we plot here R infinity, this is our unitarity constraint in TeV. So if here we have R infinity equals 1, which is just the symmetric case, this starts off at 140, and then it drops down and has this sort of shape. This would be 10 to the minus 8 here. It reaches a value of about 46 TeV, 10 to the minus 6, 10 to the minus 4, 10 to the minus 2, something like this. Yeah? This is just a plot of this function. Okay, so this applies in many asymmetric dark matter models because you have you need this annihilation after you've set the asymmetry. One counterexample, the sort of only exception I know, but which I won't discuss, is so-called cue balls as asymmetric dark matter. You can look at this paper by Shaposhnikov and Kusenko if you want to learn about those. There, I should say, okay, the asymmetric dark matter is not a fundamental particle, but a large bunch of charge, so-called non-topological soliton. Okay. So careful if you read some paper which claim, that wants to do something with asymmetric dark matter, and they set their dark matter mass to be above 100 TeV, or even a bit lower, above, let's just say 100 TeV, then we've got to question, whether there's some issue with the self-consistency. Yeah. Yes.
So in general, you must be a dark matter mass that is huge than 46 TeV.
For asymmetric dark matter with a very suppressed, let's say, suppressed anti-dark matter population, yeah? It has to be below, okay, let's say, some order 10s, 50 TeV, 60 TeV. It's just a rough argument. It won't give you an exact number, yeah?
This destroy our help in the model to detect.
Yeah. Okay, and I should say, of course, there are lots of ways around this unitarity constraint. In the case of symmetric dark matter, you have, if it's not set by the thermal freeze-out mechanism, then of course it doesn't apply. If it's a primordial black hole, of course it can be much more massive, or even something else, it can be much more massive. If you have entropy, all the assumptions we made go into this number. So if you have entropy injection, you're not going to, you're going to weaken this constraint. If you have an early matter-dominated phase while the freeze-out is occurring, you're going to change this, weaken this constraint, so on. But in the case of, entropy injection, in the case of asymmetric dark matter, you'll also dilute the asymmetry, yeah? So you'll add even more additional complications compared to the symmetric dark matter case, okay? Okay, very good. So now we've covered the annihilation of dark matter at sort of the lowest temperatures of interest for our models in detail. Now we're going to look at asymmetry generation. Okay, so what do we know? We know that omega dark matter is approximately 5 times omega visible matter, okay? And the visible matter density is set because of this asymmetry in the number of baryons minus antibaryons. Okay, now we're going to look at asymmetric dark matter models, and in many I'm going to give you sort of an overview. Yeah, there are many, many papers in the literature on asymmetric dark matter. I don't know, 500, 1,000. Okay, I don't know. In many models, this asymmetry in the visible sector can be related. You want to relate it somehow to some asymmetry in the dark matter sector. Yeah. So sort of the simplest case, and maybe even you might think it the most aesthetically pleasing, is that typically, but not always, yeah, we'll have some relation such that either the dark sector asymmetry is somehow approximately the visible sector asymmetry, yeah, up to some order 1 factors. And this will then tell you, right, that in typical models, because of this observation here, M asymmetric dark matter will be in sort of, we'll take values somewhere, just giving a range, 1 to 10 GeV or so, okay? Now it should be clear, however, okay, that this, even if you have some mechanism which sets this, yeah? But even though you set this asymmetry, you don't fully explain this, you don't explain this coincidence, yeah? Because in the relation then, in asymmetric dark matter, that the masses of the asymmetric dark matter and the proton mass, which is coming from QCD, this is not typically explained. Okay? You might think, okay, at least asymmetric dark matter is, if we're being generous, sort of the weak scale, yeah? But to explain why it's of the order of the proton mass, which is coming from QCD, is not typically done, yeah? It's a difficult problem, yeah? So then this is still somehow still a coincidence, yeah? Because of the mass of the dark matter. Okay. So that, having said that, it's still sort of interesting that, okay, you set this to be the sort of the weak scale, and we saw that we also need a bit larger than the WIMP cross-section to get rid of the dark matter antiparticles. So it's still sort of nice, yeah, that our cross-section can then typically also, let's say, easily be large enough, our annihilation cross-section, to get rid of the dark matter antiparticles. Okay. So now our picture is going to be that we start off in a symmetric, with a symmetric number of dark matter particles and antiparticles, and we're going to generate our asymmetry. So we're going to have here, if I draw here, Nx, and here, Nx bar. And now we're interested in generating this asymmetry. And then, of course, because of the annihilation that we've talked about now extensively, we're going to get rid of most of the dark matter antiparticles and the symmetric part of the dark matter particles, yeah? So then, after the annihilation, we're going to have a little remnant Nx, which can be easily of the order eta dark, and then only a very suppressed number of dark matter antiparticles. Okay. So now, we have to try and summarize like sort of group together different ways of generating this asymmetry. And luckily for me, this was done, for example, in a review paper, which you can find here. Okay? And let's follow their convention. So possibility number one is that we have a linear combination of the visible baryon number and the dark matter baryon number, which is exact. And I should say, okay, I'm going to write BV here, but at high temperatures, we should just mentally think of B minus L, yeah, because of the electroweak Phaleron. Okay? And similarly, if there's an analog of the electroweak Phaleron in the dark sector, then we also take the analog of the B minus L in the dark sector. Okay? So we have a linear combination which is exact, and linearly independent combination which is broken. Okay. Then if you have this case, it's always possible, it ends up that it's always possible to choose the charges of your dark matter fields so that B conserved is equal to BV minus B dark, and the broken combination will be BV plus B dark, okay? So showing this, there's a simple way of showing this. It's given in this review paper and also in the notes, but in the interest of times, I'll just leave it like this, yeah? It's just basically you can rescale the definition of this BV and B dark, the charges, and then find this linear, this combination being conserved and this being broken, okay? So then, now we'll generate some asymmetry in this number, okay? And call it eta. So we'll have eta broken. We'll define this in this example here, 1. Eta broken as eta, which will give us immediately from this is conserved, the first one. So then, of course, we'll get eta of B broken equals eta of B dark equals eta on 2, okay? So now, what does this imply for our dark matter mass?
Iason,
Yeah?
is it a simple, I don't know, interactions or Lagrangian that you can show? I think it's not very clear at least.
Okay, let me do the generic list, and then later on I'll show then it'll become very clear, yeah? So, yeah. Or maybe I already write one down. So let's see. Say, okay, for example, yeah? We'll look at this example more later, yeah? But say if we have a Lagrangian like, let's say we write an effective operator. Here we have a Dirac particle which is going to generate our asymmetry, couple it to the neutron operator, yeah? Like this, say, and then couple it also to some, this is a Dirac particle, yeah? Couple it also to some dark sector fermion and scalar, okay? And then you can write down you can give this some generalized baryon number, yeah? And then you'll see that you can also define a baryon number for these fields here, the generalized one. But then here, this will be like carrying B dark and this B visible, yeah? And this is Dirac, so there's no Majorana mass which would completely break everything. Okay, we'll come back to that example later. So typically in these cases then, okay, because the asymmetry in the dark matter sector, okay, yeah, I should say, yeah, this is obviously, sorry, what did I do here? Eta visible, like this. So the visible asymmetry is related, the dark asymmetry is related to the visible asymmetry. So at high temperature, of course, we should take BV to be B minus L standard model. This will be typically be the case. So then basically M dark matter, so let's say the number density of your dark matter particles after the annihilation has occurred, the number density of your visible matter, okay, your baryons, is going to be typically 0.35 to 1 times B minus L of the standard model, yeah? Which implies then, this is if the asymmetry is generated before the electroweak phase transition, and this after, when the sphalerons are switched off. So then basically in this sort of scenario, you get that M dark matter is given by the dark matter charge, the generalized B minus L charge, and the mass is about 1.6 to 5 GeV, okay? Now, before we were interested in many different masses of dark matter, so we have to see if there's a way of also relaxing this conclusion. And that comes about in examples of where the asymmetry in the dark matter is not created through this sort of process, where here the sort of visible and dark matter asymmetries are created in one single process. Options, let's say, options 2 and 3. Okay, let me write option 2 first. Option 2 is that the visible B minus L is broken during asymmetry generation. So this would be the case, say, imagine you have just a standard leptogenesis. So heavy Majorana neutrino is just creating some baryon minus lepton number, yeah? But then BD is not broken by the generating mechanism itself, but there's a transfer. So there's which creates a dark asymmetry just through equilibration of chemical potentials. So the analog in what we know, like in leptogenesis, is that we generate an asymmetry in lepton number, which is transferred through the sphaleron into baryon number. Now, generalize this, you don't have to use a sphaleron, you can use some other operator, and this will then, you create this B minus L, and then the B dark shares the asymmetry, so it's a generalized B minus L, and it takes some of the B minus L number and keeps it in the dark sector. And this transfer switches off at low T, okay? So again, it's a bit unclear, but I'll show you an example in just a few minutes, and then it'll become very clear, okay? And 3 is that BD is broken BV is not. So then you have some dark sector that's creating an asymmetry, and then that asymmetry is shared to the standard model, creating the visible B minus L, okay? So it's just two, but where the asymmetry generation is being created is, where the asymmetry is being created is instead of the visible sector, it's in the dark sector. That's all it is, okay? So these are very similar, okay? And we'll see that in this case, then you can also get, depending on the dark matter, when this decoupling occurs, when the transfer switches off, that will give us a whole possible range of dark matter masses. And 4 is sort of the anarchic case where both are broken in the generation of the asymmetry. So here, this will see an example very soon. And just to give, to show where, both B, V, and B dark are broken in the asymmetry generation. So here you can think of some, just to give an example, this comes from a paper 1101.4963. Just to give an example that will make the idea much clearer. Say we have some heavy Majorana neutrinos, like in leptogenesis. We couple this to the standard model, schematically like this, so it decays to the Higgs and the lepton, generating an asymmetry. This is just the standard type 1 leptogenesis. And it has a Majorana mass, so the B minus L is broken. And now let's say we just couple this Majorana neutrino also to some dark matter particles, yeah? Again, everything now is broken, yeah? Okay. Obviously, for the generation of this, whatever generalized particle-antiparticle asymmetry, the Sakharov conditions are going to hold, yeah? But instead of, the only change is going to be that instead of requiring baryon number violation, we need whatever generalized baryon number we're interested in creating, we need to break that, yeah? Okay. So now I'll give, out of these 4 options, here, I should say, here also the mass is, in the simplest cases, will be of the order 1 to 10 GeV, but can be much heavier. Much heavier than the proton mass is also possible, and I'll explain that in a second. And here also, because these asymmetries here, in this case, are not related at all, yeah? So the dark matter mass can take a wide range of values, yeah? They're complete, well, almost complete anarchy holes, except that you want to probably keep things gauge invariant and Lorentz invariant, and so on. Okay. Very good. So this just, this classification. Now let's give an example of, let's say, option 2, okay? And this example comes from the paper, a paper by Yanagida and collaborators, 5452, okay? Here, B minus L of the standard model is assumed generated by leptogenesis, okay? One of the authors is Yanagida, right? He wrote the first paper on leptogenesis, so it's a good, but it's a, as we'll hear more from Thomas lectures, of course, this is a very natural possibility, yeah, that it's generated at some high scale. So this will be option 2 or 3, really. I mean, because the options are closely related, yeah. So now assume there's a transfer operator given in this form, some high dimensional operator. Where this OSM is some combination of standard model fields, and this O dark matter is some combination of dark matter fields. So at the moment it's very generic, but actually you can, in a very generic way, you can find what mass of the asymmetric dark matter you expect. So it's a very nice example. For example, okay, this operator could be 1 on lambda cubed. Let's see. I messed up in the notes. So let's see. 1 on lambda phi squared. So LH squared. So this has dimension 3, so 2 times 3 halves plus 1. So this is dimension 4. No, stuffed up. 5, sorry, of course, because it's just like the Weinberg operator. And then we have a 2 here. So we have 7. So this should be cubed, yeah? Okay. Yeah, so the notes were correct. Or 1 on lambda cubed. This is the fermion example, yeah? Okay.
A comment or a question?
Yeah.
In principle, this kind of operators can be realized from option 4, right? Because you just integrate out the heavy degree of freedom.
You can also have, exactly, that's a good point. So in the option 4, there can also be transfers occurring between the sectors, yeah? That's a good point, yeah? So in that case, you'll also have washout processes occurring between the 2 sectors as well. Okay. So now, okay, we're going to look at we're going to assume this form, and we're going to derive what the asymmetry is in the dark sector and the dark matter mass, okay? So we're going to do a chemical potential analysis, okay? So we're going to assume, and this is going to tell us the dark matter mass, okay? And to do this, we need to use the fact that in the relativistic limit, the number of fermions minus the number of antifermions. So in the relativistic limit, I mean the temperature is higher than the masses of the particles. This is given by G T cubed on 6 mu on T, and times 2 for bosons. Okay? This is going to relate the chemical potentials, which we're going to find, to number asymmetries. Okay? So first of all, we're going to assume, for simplicity, that all the Yukawa interactions are in equilibrium. Okay? So then we get relations such as we get these relations. Yeah. So this just comes from the right-handed quark Yukawa, which relates, if it's rapid, this process, you get a relation between the chemical potentials of the Higgs, the left-handed quark doublet, and the right-handed up quark, yeah? Okay? So these are the Yukawas. Then we have a relation from the, so these are the Yukawas. Okay, do you understand where these come from, or should I write it out? Yeah, okay. So let's see. I gotta get the, okay, so let's see, for example, yeah. So for example, this one here, we have a Yukawa coupling, which is QL bar H dr, okay? Okay, and now assume that this will lead to some interactions in the thermal bath, and assume we're assuming here implicitly that these are rapid, so that chemical equilibrium is established. Yeah. So then, let's see. So this process will lead to something like H. If we draw a Feynman diagram, just imagine what's going on in the plasma. Say this produces a right-handed, right anti-D and a Q. Yeah. So this, then you imagine that this gives you the relation that MH equals to the chemical potentials on the fields on the right-hand side, which is MQ minus mu dr, okay? Here, this is the minus mu dr because this is the antiparticle, and the annihilations of all the gauge interactions are also in equilibrium. So the annihilations of, say, such annihilations, something like this, yeah, will keep mu dr plus mu d anti-r equals 0, yeah? So I've implicitly used that. Okay, good. So these have just come from all the Yukawa couplings. Then you also have to use we also have, imagine we're at high temperature, so the electroweak sphalerons are active. And this gives the relation MQ plus mu L equals 0, okay? And in principle, they're also the strong sphalerons, but you can check that that doesn't give you anything else, okay? I should say, we also require that the total hypercharge vanishes. So U1Y neutrality also imposes a condition on all the Yukawa couplings, which we can use later on, which you imagine that you take into account all the asymmetries you have in fermions, take into account their hypercharge, and demand that the entire universe is hypercharge neutral, yeah? And that gives you the following. I should say these sort of relations also appear in leptogenesis and so on, yeah? Okay, and the analysis in the paper, they also allow for different multiple Higgs doublets. So this is the number of Higgs doublets. Later on, you can set it to 1 if you like. Yeah? Okay. Now, we have these chemical potentials. And now, now we have to figure out what this operator is going to do for our dark matter chemical potential. But we're going to keep everything generic. We're not going to write down any specific operator yet, yeah? Later on, we can think of specific operators. But at the moment, we can keep everything general. And then we'll see a very nice result. Okay. So we suppose O dark matter has dark matter number. So the dark matter number is just defined, N dark matter is just going to be the number of dark matter particles that appear in that operator minus the number of dark matter antiparticles, okay? And for simplicity, we're just assuming a single species of dark matter, yeah? Okay, you can easily generalize it. So here we have 2 dark matter particles involved. Here we have 3. If we put instead a chi bar and change this operator, then we'd have, and change the dimension here as well, then we'd have, if we put in some, how should I write this? Chi bar, chi c, then we'd have, subtract 2 because we have then 2 dark matter antiparticles. And we're going to assume that the charge, the generalized B minus L charge of, then of course the generalized B minus L charge of this operator is going to be Q dark matter, the B minus L of the dark matter times N dark matter, okay? And then we also suppose O standard model, which is made up, O standard model, that operator is made up of standard model fields, and we're going to have NQ number, so number of quark doublets minus number of quark anti-doublets, N UR, N DR, N number of lepton doublets, N number of right-handed, right chiral lepton fields, and NH, okay? Very good. So this then relates, okay, we need this whole thing to be a singlet under hypercharge, yeah? So that gives us the relation that, NQ on 6 plus 2 NUR on 3 minus N DR on 3 minus NL on 2 minus N ER on plus NH on 2. So these are just like the numbers appearing weighted by the hypercharge equals 0. Okay? And then finally, we also want this to be a singlet under the B minus L, the generalized B minus L, yeah? Otherwise, we'll have washout of the B minus L asymmetry we created. And this final condition then gives you that NQ on 3 plus NUR UR on 3 plus N dr on 3. So it's just the same relation before, but we're weighting by the B minus L charge. Okay? So these are all the standard model B minus L charges which could appear. And then we're going to have Q dark matter, N dark matter. So in a way, this sort of defines what Q dark matter is. This is going to be 0, okay? Then now you have a whole system of equations, yeah? And we're going to just jump ahead. It's a whole system of linear equations relating all these chemical potentials which appear and these numbers which appear in the operator and so on. But in the end, combining everything, one gets a very neat result. One finds that the chemical potential that the dark matter attains is just -10 plus the number of Higgs doublets, which in the simplest case we can set to 1. Q dark matter mu L. So it just depends on the B minus L charge of the dark matter, and everything else drops out. And mu L is the chemical potential of the lepton doublet, which can be related to the B minus L asymmetry. So it's very neat, yeah? And what this tells you...
So just to be clear, you're assuming these are in equilibrium, no? Thermal equilibrium.
All I assumed was that this is in equilibrium, yeah? So then for these individual ones, then you can set the Q, you can read off what Q B minus L is of your dark matter here, depending on this power here, yeah? Okay. So then, okay. Then you use, okay. I should write this, yeah. I should write this. Okay. Very good. Yeah. So then one can also use that the baryon number asymmetry is related to, can be by definition related to some chemical potential, which is just chosen for convenience, which will be 3, 2 mu Q plus mu. I should write this. This is the lepton doublet chemical potential. So I should have put here lepton doublet chemical potential everywhere to distinguish this from the chemical potential of the lepton asymmetry, okay? And yeah, so in your notes, if you're taking notes, replace the mu L in the Yukawa and the sphaleron with this, yeah? It's just the chemical potential of the lepton doublet, yeah? While this is the chemical potential, to make things clearer, let me write this with a tilde, yeah? That otherwise it'll be very confusing. So this is just the standard model lepton number, but I wrote it with a tilde so that things won't get messed up, okay? And this with the tilde is just 3, 2 mu L that we had before, which is that of the lepton doublet, plus mu ER. And in the end, we know what B minus L has to be to get the correct baryon abundance. You just take into account the sphalerons, so that because so putting everything together, then the N B minus L of the dark matter, when you put everything together, it's equal to 22 6 plus NH over 7 on 66 plus 13 NH. So this just comes from solving that system of equations for all the chemical potentials that can all be related to a single one, which you can take to be the chemical potential of the NB minus L, NL. Okay. Q dark matter squared NB minus L of the standard model. Okay. And this is basically NB of the standard model, taking into account the sphalerons like this. Is that right? Yeah. Okay. So in the end, when you put everything together, you find that M dark matter, you find a simple relation is approximately 5.1 GeV over Q dark matter. And just with this generic assumption of a transfer operator, you find this relation. This is for when this operator decouples above T electroweak, 130 GeV or so, and if we use the Sphaleron relation, but there are similar relations, you get a mass of 7.1 GeV over Q dark matter for T decoupling smaller than T electroweak. Okay, so you have this very nice relation. Now, what we've done here, you see the dark matter is again of the order of 5 GeV or so, but it scales inversely with the dark matter charge, rather than in option 1, which I wrote down briefly the relations where it scaled as the dark matter charge. Yeah. Okay, so now we're still left without choosing a very large Q dark matter, or we're still left with a sort of light dark matter. So why did we bother discussing the unitarity constraint and so on? Well, simple. So what a simple change can actually give us much heavier dark matter to this sort of scenarios, okay? So here we assumed the dark matter, or everything here was approximately massless compared to the temperature, yeah? So we had this relation, but this relation where the asymmetry was like T cubed on 6 times the chemical potential over the temperature, yeah? But now, and we assumed this decoupling occurred when everything, all the particles, not just the standard model, but the dark matter was approximately massless. So the opposite case for non-relativistic decoupling you can see, for example, this paper by Lisa Randall and, sorry, I forgot the second author. But he's also a famous guy, but I just forgot. So from this paper, you can see the argument is the following. Say we have some sharing of the chemical potentials between B minus L and the dark matter B minus L. Now, in the non-relativistic limit, the particle asymmetry, the scales the following way. So the particles now, the dark matter particles X now become Boltzmann suppressed. So if they disappear from the thermal bath, they don't take much of the B minus L charge to their sector, right? So this, you have this sort of relation, So now, but say they're still in equilibrium, this some transfer operator is still active when these things are getting Boltzmann suppressed, The chemical potentials are still related in a similar way, But now the number density of the dark matter becomes suppressed, So then to compensate, you need heavier dark matter, So to get, so in general, to get omega dark matter approximately omega B with mu dark matter of the same order as the baryon chemical potential, in general, two solutions are possible, You either have this relativistic decoupling, options. Relativistic decoupling, where we saw the precise relations, let's say there, with certain minimal assumptions, but let's say the dark matter mass is then most naturally of the order of a few GeV or so, 5 GeV or so, or non-relativistic decoupling, where now m over the decoupling now occurs when mx over t is of the order of 10 or so, You get this Boltzmann suppression. These are just some rough numbers, not the precise. And then you get that your asymmetric dark matter is then sort of naturally of the TeV scale, So then here, in this case, M asymmetric dark matter, much greater than the proton mass is also possible, And in the fourth scenario that we mentioned, of course, the asymmetry in the dark matter could be, in principle, depends on some branching ratio of some heavy field into the dark matter sector, some other CP violating phases. The asymmetry could be very small, in which case you can push this up to tens of TeV and so on, as long as you don't hit the unitarity constraint. Okay.
Just a comment.
Yeah.
Just to be clear, I think these two results are different. I think one is because you use the B minus L, the other use the B, right? The B conservation. I think it's probably not clear for the
I mean, here, this one, and then the electroweak sphalerons aren't active, and that's exactly right. Sorry, that's a good comment. It's dealt with in that paper, so if you're interested in this case, of course you can follow through. Okay. So now we sort of had a look at this. Now I wanted to go back to this case one and give you a rundown of a a bit more of a rundown of a model for case 1, where the asymmetries are generated in the same sort of process, and they're very closely related. And in that example, we'll also see some interesting pheno. So some possible exotic signature, a model-dependent one, but an exotic signature for asymmetric dark matter. I won't have time to cover all of it, but we can continue tomorrow. Okay, this is this example of case 1 or option 1, which I wrote down the Lagrangian briefly before. This model is called Iliogenesis 10008.2399. Okay. So the Lagrangian here is given by, we're going to generate the asymmetry here through the decay of these Dirac fermions X, heavy Dirac fermions. They have couplings to the, effective couplings to the neutron operator. Yes, this is U1 gauge invariant, and also SU3. And then we're going to have 2 dark matter species here. And these are going to be this is going to be our fermion, and this is going to be a scalar, and these are going to form our asymmetric dark matter. Okay. So now we'll generalize baryon number, or even baryon minus lepton number if you like. And the baryon, let's just say baryon number for simplicity. We can imagine this may be occurring after the sphalerons are no longer active. So obviously we're going to have here our generalized B minus L, or baryon number with now dark baryons By and B phi. This is conserved. Yeah? Okay. So we give these baryon number 1. X can decay to D bar. Sorry, yeah. Yeah. So we'll look at the Feynman diagrams in a second. Yeah. So now, to ensure stability of the, we have to ensure. Okay, we have at low energies, we have neutrons, protons around, and we also have our dark matter phi and y. And we don't want these to decay into each other, yeah? So they're both around, okay? So if we have the masses m y minus m phi absolute value less than the proton plus the electron mass, and if we have these within this range, which is possible, then the following decays are kinematically disallowed. So P, proton going to y bar plus phi star plus E plus plus nu E, and also neutron going to y bar plus phi star through this heavier particle X. Yeah? These are kinematically disallowed. So are the decays of, so the visible matter which carries baryon number won't decay into dark matter, right? Which carries the generalized baryon number, the anti-dark matter. Okay, and phi is that P bar, yeah, E plus neutrino. So we have these are all kinematically disallowed. So the dark matter and the baryons are stable, okay? Otherwise, they could decay through these operators. Okay. So first of all, we need a complex phase to generate the asymmetry. So we have a complex phase in these couplings. Not psi, it should be zeta. Zeta 1, zeta 2. This contains a physical phase. Okay. And now we're going to assume, for the annihilation, once we've generated an asymmetry in the dark matter, for the annihilation, you can assume some hidden U1 dark. Yeah? So these things can annihilate into dark photons, okay, to get rid of the symmetric component. Okay, now we'll turn to the asymmetry generation. So the possible decays we have. So let's see. Yeah. X bar goes to anti. Yeah. We have these decays. So you see, this final state carries visible baryon number, and this final state can carry dark baryon number, yeah? This final state carries, this final state carries negative baryon number 1, and this dark baryon number -1. Okay, now we assume that these decays happen out of equilibrium, and then the CP violation will create an asymmetry in the probability of x1 going to UDD and x1 bar going to U bar, D bar, D bar, okay? And the Feynman diagrams responsible for this are the following. But I say, if there's an asymmetry in this decay, there has to be a sort of opposite asymmetry in this decay so that the total decay rate of the X1 remains equal to the total decay rate of the X. The antiparticle has to have the same decay rate, the total decay rate, summing over the final states as the particle. Okay, so the asymmetry arises from the CP violation, arises in the decay, arises through the interference between this tree-level decay with this effective operator and the loop decay. Okay? Now, for this to give you a CP violation, this has to be, you have to be able to cut this diagram and kinematically put these particles on shell. But this is possible because X1 will be heavier than Y bar and phi. Yeah? So you can calculate this asymmetry. Okay, and it scales the following way. Yeah, good. And this, in terms of the underlying parameters, because of this effective operator, it depends sensitively on the mass here. Imaginary. So if you take this scale of this capital M, which is suppressing that operator, if you take that up too high, then obviously you're going to not have enough of an asymmetry in your decay. So the couplings, you can find the couplings by considering the interference between these two diagrams. So you just write in the couplings and you should find this. And because of this factor of mx2, there's an x2 particle here appearing, yeah? So from the fermion propagator, that's why you get this mx2 here. It's in the limit where, this is in the limit where 1 on mx2 minus mx1 is approximately 1 on mx2. So it's some small hierarchy there. Okay. So with this sort of setup, then you can create an asymmetry in the baryons and also in the dark matter sector. Okay. Okay, very good. So that's, let me see. So we're gonna, so in the end, if these decays, I can maybe go on tomorrow. If these decays are out of equilibrium, then you can create some net UDD and some net, because this decays preferentially compared to this decay, but then the opposite, to keep the decay rates equal, this has to decay preferentially in the same way compared to this, yeah? So you create some UDD and net UDD and net Y phi, okay? One more assumption, that went into this formula is that the decay rate of X1 is given somewhat, it decays somewhat preferentially into the two-body final state. So that's why they have this zeta 1 from this gamma x1 down the bottom, zeta 1 squared. That's just from the tree level decay. Okay. So that's it for today.
Any questions from the audience?
Yeah, yeah. So it was, yeah.
Okay, I have a comment. So in this scenario, you also have to assume the dark sector has some fast interactions to annihilate the symmetric component.
Yeah, so that's right. So these things are assumed charged under a U1 dark symmetry, gauge symmetry. Yeah. So by having opposite charges, the net, this can be gauge invariant, this operator. So then, and the net charge, the net dark electric charge in the dark sector is 0, yeah? Like in the standard model, we have more protons than antiprotons, but we also have more electrons than anti-electrons to balance the charge, yeah? So then the annihilations are exactly given by such diagrams. We saw similar ones before, yeah? So let me call this dark gauge boson Z prime now, yeah? You can write down a Stuckelberg mass for it, yeah? If you like. Or if you keep it massless, then you have some dark radiation, which I think by now is actually in conflict with delta and effective constraints. But the fermion will annihilate like this, and then of course you'll get diagrams for the scalar. You'll have such diagrams as well, yeah, and also for the scale, the T-channel one. Now this dark gauge boson will mediate. Let's say you don't want to run into ineffective constraints, so you give it a mass, then you need it to decay. You can make it decay back into the standard model through a kinetic mixing. So let's put the kinetic mixing in. You go to via the standard model gamma to E plus E minus and so on. The consequence of that is that you want this decay to be rapid enough so that you're not in conflict with BBN constraints and so on, and C and B constraints. And to do that, you have to, you need this kinetic mixing parameter here to be large enough. Once you do that, you now have a Thanks for the question, actually.
A long answer.
Once you do that, you have your dark matter can now interact via this Z prime with nucleons, yeah. Similar for the phi, yeah. So now. And remember, the Y and the phi are sort of light, yeah? Like some few GeV or so, yeah? So this Z prime also, which has to be lighter, so the annihilation is possible, is also light, yeah? So you have, depending on this kinetic mixing, now you have a large direct detection cross-section. And for the mass range of interest, yeah, the strongest, see, this is so, it's light, yeah? So in direct detection experiments, the heavy nucleons like the heavy nuclei, sorry, like xenon, they lose sensitivity there. Yeah. So the most stringent, up-to-date limits come from dark side 50 actually. The updated limit is from June of this year, and it's still viable. It's still viable, given all the other constraints. So I should say the masses here are the masses of these individual particles, given these kinematic constraints and given the abundances we have, they're like 1.7 to 2.9 GeV. Yeah, the y and the phi, and the z prime has to be lighter. Yeah.
Okay. Any questions? Okay. I guess we can go for lunch. And thanks again, Iason.